In today's video, we are going to learn about hidden Markov model algorithm with implementation examples. Introduction. Hidden Markov model HMM is a statistical model that is used to describe the probabilistic relationship between a sequence of observations and a sequence of hidden states. It is often used in situations where the underlying system or process that generates the observations is unknown or hidden. Hence, it got the name Hidden Markov model. It is used to predict future observations or classify sequences based on the underlying hidden process that generates the idea. An HMM consists of two types of variables: hidden states and observations. The hidden states are the underlying variables that generate the observed data, but they are not directly observable. The observations are the variables that are measured and observed. The relationship between the hidden states and the observations is modeled using a probability distribution. The hidden Markov model is the relationship between the hidden states and the observations using two sets of probabilities: the transition probabilities and the emission probabilities. The transition probabilities describe the probability of transitioning from one hidden state to another. The emission probabilities describe the probability of observing an output given a hidden state. Hidden Markov model algorithm. The hidden Markov model algorithm can be implemented using the following steps. Define the state space and the observation space. The state space is a set of all possible hidden states, and the observation space is the set of all possible observations. Step 2. Define the initial state distribution. This is the probability distribution over the initial state. Step 3. Define the state transition probabilities. These are the probabilities of transitioning from one state to another. This forms the transition matrix, which describes the probability of moving from one state to another. Step 4. Define the observation likelihoods. These are the probabilities of generating each observation from each state. This forms the emission matrix, which describes the probability of generating each observation from each state. Step 5. Train the model. The parameters of the state transition probabilities and the observation likelihoods are estimated using the Baum-Welch algorithm or the forward-backward algorithm. This is done by iteratively updating the parameters until convergence. Step 6. Decode the most likely sequence of hidden states given the observed data. The Viterbi algorithm is used to compute the most likely sequence of hidden states. This can be used to predict future observations, classify sequences, or detect patterns in sequential data. Step 7. Evaluate the model. The performance of HMM can be evaluated using various metrics such as accuracy, precision, recall, or FI score. To summarize, the HMM algorithm involves defining the state space, observation space, and the parameters of the state transition probabilities and observation likelihoods. Training the model using the Baum-Welch algorithm or the forward-backward algorithm, decoding the most likely sequence of hidden states using the Viterbi algorithm, and evaluating the performance of the model. Implementation of hidden Markov model. key steps in the Python implementation of a simple hidden Markov model using the HMM library. Example 1, predicting the weather. Problem statement: given the historical data on weather conditions, the task is to predict the weather for the next day based on the current day's weather. Step 1, import the required libraries. The code imports the NumPy, Matplotlib, Seaborn, and the HMMLearn library. Step 2, define the model parameters. In this example, the state space is defined as a state which is a list of two possible weather conditions, sunny and rainy. The observation space is defined as observations, which is a list of two possible observations, dry and wet. The number of hidden states and the number of observations are defined as constants. The start probabilities, transition probabilities, and emission probabilities are defined as arrays. The start probabilities represent the probabilities of starting in each of the hidden states. The transition probabilities represent the probabilities of transitioning from one hidden state to another, and the emission probabilities represent the probabilities of observing each of the outputs given a hidden state. The initial state distribution is defined as state underscore probability, which is an array of probabilities that represent the probability of the first state being sunny or rainy. The state transition probabilities are defined as transition underscore probability, which is a 2 cross 2 array representing the probability of transitioning from one state to another. The observation likelihoods are defined as emission underscore probability, which is a 2 cross 2 array representing the probability of generating each observation from each state. Step 3, create an instance of the HMM model and set the model parameters. The HMM model is defined using the HMM categorical HMM class from the HMM Learn library. An instance of the categorical HMM class is created. The number of hidden states set to n underscore hidden underscore states, and the parameters of the model are set using the start prob underscore comma transmat underscore and emission prob underscore attributes to the state probabilities, transition probabilities, and emission probabilities respectively. Step 4, define an observation sequence. A sequence of observations is defined as a one dimensional NumPy array. The observed data is defined as observations underscore sequence, which is a sequence of integers representing the corresponding observation in the observations list. Step 5, predict the most likely sequence of hidden states. The most likely sequence of hidden states is computed using the prediction method of the HMM model. Step 6, decode the observation sequence. The Viterbi algorithm is used to calculate the most likely sequence of hidden states that generated the observations using the decode method of the model. The method returns the log probability of the most likely sequence of hidden states and the sequence of hidden states itself. This is a simple algorithm of how to implement a basic HMM and use it to decode an observation sequence. The HMM Learn library provides a more advanced and flexible implementation of HMMs with additional functionality such as parameter estimation and training. Step 7. Plot the results. Output. Finally, the results are plotted using the matplotlib library, where the x-axis represents the time steps and the y-axis represents the hidden state. The plot shows that the model predicts that the weather is mostly sunny with a few rainy days mixed in. Example 2. Handwriting recognition problem statement. Given a data set of handwritten characters, the task is to recognize the character based on its shape. In this example, the state space is defined as states, which is a list of 26 possible characters. The observation space is defined as observations, which is a list of 8 possible observations representing the direction of the stroke in the handwriting. The initial state distribution is defined as start underscore probability, which is an array of probabilities that represent the probability of the first state being any of the 26 characters. The state transition probabilities are defined as transition underscore probability, which is a 26 cross 26 array representing the probability of transitioning from one character to another. The observation likelihoods are defined as emission underscore probability, which is a 26 cross 8 array representing the probability of generating each observation from each character. The HMM model is defined using the HMM multinomial HMM class from the HMM Learn library, and the parameters of the model are set using the start prob underscore, transmat underscore, and emission prob underscore attributes of the model object. The sequence of observations is defined as observations underscore sequence and is an array of length 11 representing 11 strokes in the handwriting. The predict method of the model object is used to predict the most likely hidden states given the observations. The result is stored in the hidden underscore states variable, which is an array of length 11 representing the most likely character for each stroke. The code represents the algorithm. Output. Finally, the results are plotted using the plot function from matplotlib, which shows the probabilities of hidden state for each stroke in the handwriting. In conclusion, hidden Markov models are powerful statistical models used to model sequential data. They have a wide range of applications, including speech recognition, natural language processing, and bioinformatics. When they have some limitations, these can be addressed through the use of more advanced models. HMMs are an important tool in the field of machine learning and will continue to be an area of active research. Thank you.